So this lecture is probably the most important from the kinematics unit. Some would argue it's the most important for the entire grade 11 university preparation physics course. We are going to talk about the 5 Newtonian equations of motion. The title of the lecture is Motion with Uniform Acceleration. Uniform acceleration implies that the acceleration is not changing. So these equations of motion that we're going to look at are equations where our acceleration is a constant non-zero value. When we have a zero value for acceleration, things get a lot simpler. We can analyze them using just the velocity equals distance over time equation. But when we have a change in velocity, we have an acceleration, and there are actually 5 equations of motion we can use to understand how motion will occur using those 5 equations. So let's, before we get into that, before we introduce those 5 key equations, let's do a little graphical analysis here. We can use graphical analysis to solve a physics problem, but we might find that there's enough information to solve something just in an algebraic way. So here's a question. It says, or it doesn't say anything, but implied from the question is, we have 3 displacements, a d1, which is 5 kilometers east, d2, which is 4 kilometers south, and a d3, which is 8 kilometers west. So those 3 displacements together get us from a start point to an end point. And you see the resultant displacement is equal to 5 kilometers, 37 degrees west of south. So it's south 37-degree turn towards the west. So we could do this graphically, but there is an algebraic way to solve this, which is a bit more convenient than doing a graphical analysis. And to do it algebraically, we would use these 5 equations of motion. They're sometimes called the Newtonian equations of motion. They all imply that a is not changing, so acceleration does not change, it's uniform, and a is a non-zero value. So here, these equations are written here with the arrows and the deltas, the arrows to imply vectors, the deltas to imply a change. Quite often we just omit those because it just makes it easier to write. And you will see, aside from this point here, for the rest of the course, I'll be writing them without the deltas and without the arrows to indicate that they're vectors, just because it makes things faster to write, and you'll commonly see them in that way. Now, I did mention when we have uniform motion, that's when acceleration is equal to 0, things are a lot simpler. We can analyze motion using v equals d over t, which is one simple equation to use. That's something to keep in mind. The 5 equations are used whenever we have a non-zero value for acceleration. And you'll see the subscript I and F. Those are for initial velocity and final velocity. Sometimes we use a 1 and a 2, 1 for initial, 2 for final. The equations that are written there are usually written to define the distance or the displacement. But there are 2 that are written in other forms. Vf equals Vi plus At, and Vf squared equals Vi squared plus 2Ad. Now, you might think, how am I going to decide which of these 5 equations am I going to use? Well, I'll teach you that as we go through our sample problems. But in general, you're going to be given a problem with 3 pieces of given information. One variable you would need to solve for, and one variable you might not be interested in. You would basically use the equation that includes the 3 given variables and the variable you need to solve for. And then you would need to sometimes rearrange that equation to solve for the value you're trying to solve for. So that is how that's how you would essentially do a physics problem. I will go through that with you with our first question. Here it says that we have a sports car that is traveling on an on-ramp. It has a velocity of 20 meters per second, and it ends up accelerating at 3.2 meters per second squared for 5 seconds. We're asked, what is the displacement of the car? So what we have for this question is we are given the velocity, the initial velocity, so I'm going to write VI. We are also given the acceleration, which is A, and we're given a time. We're asked to find the displacement. So RTF means required to find. Oops, my camera just lost. Required to find displacement, which is D. So let's pull up our 5 equations of motion. I've got them written here. Which one of these equations includes, let's see if I can put these both on the same page here. Which one of these equations includes VI, A, T, and D? Well, here we have D, we have VI, we have VF, which we don't need, and we don't have any A. So we can't use equation 1. Here we have D, VI, T, A, and T. So we have the VI, we have the A, we have the T, we have the D. So this is the equation we would use. We don't need to check the others because we know this doesn't include, this includes a VF, which we don't need, and it doesn't include a VI, which we have. This includes a V2 or a VF, which we don't have. And this includes another VF or V2. So we'll need to use that second equation, which is D equals VIT plus 0.5. Sometimes it's written as a half. AT squared. I'm going to show my substitution with brackets. So VI in this case is 20.0 east. T is 5.0 plus 0.5 A, which is 3.2 east. And my T squared is going to be 5.0 squared. So let me pull up my calculator on the screen. And we'll calculate this. 20 times 5 plus 0.5 times 3.2 times 5 squared equals 140. So D equals 140 meters to the east. That's our first problem. Let's move on to the second one. Here we have a sailboat, and this sailboat has a uniform acceleration. It goes from 6 meters per second north to 8 meters per second north, and it accelerates at 0.50 meters per second north. What's the displacement of the boat? So let's write down for question 2 our given information. We're given VI, we're given VF, we're given A. We are required to find the displacement, D. So here we're going to look at our 5 equations again. Let's see if I can get our givens on the screen at the same time. I'm gonna have to move this over. So we have the VI, the VF, and the A. We have to find D. So which equation? Let's see. This one has VI, VF. It has D. It's got T. We don't need T. It doesn't have an A. This one has VI. It's got T. We don't need T, so we can forget that one. This one here has a T. We can't use T because we don't have it. Lastly, here, this one's got a T. It doesn't have a VI. Or sorry, it doesn't have a D, which is what we need to solve for, so we can't use that one. We're going to have to use the last equation. VF squared equals VI squared plus 2AD. And we're going to have to use some algebra to rearrange that. So let's write this down. VF squared equals VI squared plus 2AD. Well, we need to isolate the D. So let's start by writing this term on the left side, or sorry, this entire thing here on the left side of our equation. Then I'm going to move the VI to the other side. So 2AD equals VF squared minus VI squared. Then I'm going to divide by the 2 in the A. So D equals VF squared minus VI squared over 2A. D equals VF in this case is 8.0. I'm going to drop the N because they're all facing the north direction. VI is 6. I have 2, and then I have my A, which is 0.50. So let's turn the calculator on. Oopsie daisy here and see what we got. 8 times 8 plus, or sorry, minus 6 times 6. That's going to be a numerator of 28 divided by 2, also divided by 0.5. We have a D of 28 meters. And because all of our values were north, our answer here is north. And another thing I'm going to do from now on, and I expect you to do on quizzes and tests, is to box your solution when you have your written work so that it's easier to find. Let's go on to our next question. Here we have a football player initially at rest, accelerates uniformly as she runs down the field. She travels 17 meters east in 3.8 seconds. What is her final velocity? Okay, this one's a bit trickier because it may appear that we don't have enough information. Because if I do my givens, let me move this here. When I write down my given information, I have a displacement. I have a time. I'm required to find the VF. But what else do I have? I don't have acceleration. It doesn't appear that I have initial velocity. Although, reading the question again, I see that it says she's initially at rest. So I do actually have a VI. In this case, the VI is 0. So now let's look. I need to find the equation that includes everything but A. So that is my first one here. D equals VI plus VF over 2 times T. Notice that every other equation includes an A, and because it includes an A, it's missing either a given or the thing we need to solve for, which is, in this case, the final velocity. So D equals VI plus VF over 2 times T. So I need to change this equation into an equation that solves for VF. So the first thing I'll do is I'll multiply both sides by 2. 2D equals VI plus VF T. I need to get rid of this T, so I'll divide both sides by T, VI plus VF. Now to get the VF by itself, I have to move the VI to the other side. So this ends up being VF equals 2d over t minus vi. And now I can solve 2 times 17 over the time, which is 3.8, minus my velocity initially, which is 0. So I have Vf equals, let's turn on the calculator, 2 times 17 divided by 3.8. We have 8.95, but we'll just write down 8.9 meters per second east. And I'll box that solution. Okay, last one we'll look at here. We have a dart being thrown at a target, and it says here the dart has an initial velocity of 37 meters per second. It ends up coming to a rest in 50 milliseconds. So we have to find out what the acceleration of the dart is and how far the dart penetrated into the backstop. So let's look at this question here. First, let's move this so we can see the full question. Okay, our dart in question 4, we're asked two things, which is common for these types of questions because there are two things that you could be required to find. There's two unknown pieces of information. What we're given is the initial velocity of the dart and the time. We're required to find, for part A, we're required to find the acceleration A. But I can't solve anything unless I have three pieces of information. So, reading the problem again, it says that the dart comes to rest, so it means that its final velocity is 0. Sometimes you can write that at your given. So we write our VIRT, we can write our VF equals 0. So, pull up the list of equations. What is it that we have that involves A, that involves VF, VI, and T? That looks like this equation here. VF equals VI plus AT. So if VF equals VI plus AT, and we need to solve for A, we have to rearrange this equation. And I'll rearrange this one a bit quicker. VI moves to the left side, that makes it VF minus VI. And then we divide by T. VF minus VI divided by T. VF is 0. That means that VI is going to be negative here. Minus 37 east. I'll include the direction because we are dealing with having it negative, so it could change. Our time is 0.050. Well, if I put this in my calculator, I will have a negative solution. So we'll see here that negative 37 divided by 0.050 is negative 140. So A equals, negative 740. And that would be in the east direction. Well, I'm going to, I'm just going to do it up here because I ran out of space. I'm going to write that as 740 meters per second squared west in this case. Just because my direction was initially given as east. For a question, if you were given a question like this and you weren't given any direction, your velocity would have to have a direction, so it would be acceptable to have a negative answer. In this case, I'm just writing it as a positive answer by changing the direction. The next part of this question, though, 4b, this has the same givens, but in this case you're required to find something different. Here you're required to find the displacement, how far into the board you go. Now it's a good practice to not use the value we just solved for, not to use this A when solving for my D, unless it's necessary. The reason why is because if I made a mistake here, I could then carry on that mistake there. So if you're ever given a question where you have two parts, it's good to go back to your original givens. Try to see if you can solve it with those original givens first. So let's, sorry, the calculator was still on. Let's look at this problem. We are trying to find D, and we have VI, T, and VF. So looking at our equations, we're trying to find D. We're looking for the equation that doesn't include A. That's our first one. So D equals VI plus VF over 2 times T. The good thing is we don't need to rearrange it. That gives us initial velocity is 37. We don't need to put plus 0. We're fine with that. We just put over 2. And our time, 0.050. So here D equals, turn the calculator on, we have 37 over 2 times 0.050. And we have a displacement of 0.925. Or let's round it to 0.93 meters east, or 93 centimeters.